Hi Year 12, we will look at your paper 1 questions in this video. There are SL and HL questions in here. I've indicated next to the question which SL question they are, so just make sure that you've got the right question. So remember, it's a non-calculated paper. Question 1, you have a ball that is 50 grams plus or minus a gram moving with a speed of 25 metres per second plus or minus 1 metre per second. What is the fractional uncertainty in the momentum? So firstly, we need to think about what momentum is. It's mass multiplied by velocity. If we multiply data, we know that what we need to do is add the percentage uncertainties. We also have the absolute uncertainties given to us rather than the percentages. So the first thing we need to do is work out the individual percentages. So you just take the absolute uncertainty, divide it by the value, times 100 to get it as a percentage, and so you can see that the percentage uncertainty in the mass is 2% and the percentage uncertainty in the speed is 4%. When you add those together, that tells us that the percentage uncertainty in the momentum is going to be 6%, and as a fraction of 1, 6% is 0.06, so that gives you answer C. Question 2 is deriving fundamental units for power. So power is energy divided by time. Energy is work done, which is force times distance. Force is mass times acceleration, so I can express power as mass times acceleration times distance divided by time, and then I use my knowledge of those units to get power's fundamental SI units. So mass is in kilograms, acceleration is meters per second squared, distance is meters, and then 1 over time is seconds to the minus 1. I've got 2 masses, because remember that these are effectively ones here. So I've got kg m2 s minus 3 gives me answer D. So in question 3, we've got 2 sets of data, circles and squares. The size of the error bars are the same for all points. Now we know that the error bars indicate the absolute uncertainty in our y values, and we can see that they are the same size for the circles and the squares. So we know that fractional uncertainty is the absolute uncertainty of a value divided by the value itself, and we know that we can see for the circles all of the values are shifted up compared to the squares. The circles are bigger. So therefore, although they have the same absolute uncertainty, there must be a larger fractional uncertainty for the values that are smaller, and that's for the squares. So that should give you answer D. Question 4 then is just a recall question. That should be a 2-second job, which is good because you don't have lots of time on this paper. So it's good to see questions like this. You should just remember that an amp is a fundamental unit. I've proved to you that joules, newtons and volts are not with equations, and you can hopefully see there that clearly there are multiple fundamental units for each of those. So question 5, aiming for the centre of a target, an archer fires arrows which produces a pattern of hits as shown below. The pattern suggests the presence of. Now remember, systematic uncertainties in data are where we've got consistent errors that occur each time because we're either doing our method wrong but doing it wrong in the same way each time, or if there might be a 0 error on a piece of equipment, and so all of the values are off by a certain amount because they're not where they should be. And so obviously when we have a centre of a target that we're aiming for, if all of them are consistently to the top right, we're consistently making that error. So we can see a systematic uncertainty there. A random error is less predictable by nature of the name random. We've got different error issues, and we can see a spread of results up at the top right. They don't all hit the same point. And so that accounts for the random uncertainties there. Question 6 is energy stored in springs. So note that this is a different question number for SL. An object of mass 1 kilogram hangs from rest from a spring, has a negligible mass and a spring constant of 20 newtons per metre. So I can work out the extension by using F equals kx, rearranging. Extension x is the force over the spring constant. So I know that when I hang a 10 newton weight, or in this case it's a 1 kilogram mass, which is obviously equivalent to 10 newtons, because it is a calculator paper. Obviously if it was paper 2 you would use 9.81, but remember that because it's non-calculator we can say that G is 10. So therefore I get an extension of half a metre. And then elastic potential energy stored in a spring is a half kx squared, and now I have all of my values. I plug them in. You can see my working here and you will get 2.5 joules. So question 7HL or question 8SL. A ball rolls on the floor towards a wall and rebounds with the same speed and at the same angle to the wall. So what is the direction of the impulse applied to the ball by the wall? So remember, we can always split vectors into horizontal and vertical components. Okay, and again, same here. So you can hopefully see that the vertical component remains unchanged. It's down. The angles are the same, so we know the value is going to be the same. So we don't have a change in momentum in the vertical plane. We only have it in the horizontal plane. Now the horizontal component initially was to the right, and at the end it's to the left. So therefore we've got momentum changing to the left, and impulse is changing momentum, so we just need to choose the one to the left, which is D. Okay, this one I immediately started labelling up, because that's the kind of thing I do before I even bog myself down with the wordiness of the question, so that I have a clear picture of what's going on, but it actually wasn't needed. An object of mass m is sliding down a ramp at constant speed. That is crucial, so don't underestimate the power of the words hidden in the sentences. If we have a constant speed, we know we have no change in kinetic energy. Okay, we're falling down though, therefore we are losing gravitational potential energy, but instead of it being converted to kinetic energy, we know then that all energy must be transferred to thermal energy due to friction. And so we've got whatever the loss in GPE is must be equal to the total energy transferred into thermal energy, and you just choose MGH there. Question 9 then. A block of weight W slides down a ramp at a constant velocity. Again, that's crucial. It tells us that we have no resultant force. It means we have equilibrium. It means we should be able to close our vector triangle. A friction force acts at the bottom of the block, a normal reaction N, and the weight down. So you can get your ruler out, you can measure these, you can consider the fact that we want a closed vector triangle. I've done a rough sketch for each of them to show you that we're not closing the triangle with A, B and C. And then the thing to remember here is that the horizontal component of the normal is going to be equal and opposite to the horizontal component of the friction, so there's no resultant force horizontally. And then the vertical component of N plus the vertical component of F stacks up to give you the same vector value up as we have down from the weight. They cancel each other out, so therefore the resultant of this is 0. I can also pick this up, move it around and make a closed vector triangle. Okay, question 10. I've actually done my working at the bottom, so I'll shift backwards and forwards. Two forces act along a straight line on an object that is initially at rest. One force is constant, the second is in the opposite direction and proportional to the velocity of the object. So I've just labelled this as F1 and labelled this as F2 just to make life easier, so I don't have to be very, very wordy, and I know that it's proportional, F2 is proportional to V. So let me just put that here. We know that as V increases, F2 will increase because they are proportional to each other. So initially, when it's at rest, we don't have F2 because V is 0, so F2 must be 0. So we have a resultant force which is F1, which is over here, acting to the right. Okay, so that tells us that the object initially is accelerating to the right with the maximum possible value. But as that happens, obviously the velocity is increasing. And as the velocity is increasing, this force here is also increasing. Now, that's in the opposite direction to F1, so the resultant force on the object is now going to be the difference between F1 and F2. And F2 is increasing as V is increasing, so the resultant is decreasing. Okay, so therefore the acceleration value is decreasing. Now, don't confuse that with velocity. The acceleration rate is decreasing, but we still have a positive acceleration. So we still have velocity increasing, it's just not increasing at the same rate anymore. Okay, so we still have V getting bigger and bigger. So we've still got velocity moving from 0 upwards to a maximum. At a certain point, the velocity will be large enough such that the force here is equal to the force here. The resultant force will then be 0 and we'll have 0 acceleration. And at that point we will have reached our maximum speed. Okay, and so we have Vmax occurring when F2 is equal to F1. Okay, and now because we don't have any resultant force, we're not going to get a change in velocity and F2 will stay stable. So the velocity increases from 0 to a maximum. Question 11. Which graph correctly shows how the acceleration of a particle undergoing simple harmonic motion varies with its displacement? Well, HL, you are told that A is minus omega squared x. SL, you know that A is proportional to minus x. Either way, we've got A on the y, we've got x on the x, so therefore y must be proportional to minus x, and that's obviously this graph, or at least it's proportional to. So you should have just spotted that one straight away. Okay, 12 for HL, 14 for SL. The frequency of the first harmonic in a pipe. Well, a pipe is open at both ends. It's being measured. An adjustment is made which causes the speed of sound in the pipe to increase. What is true for the frequency and the wavelength of the first harmonic when the speed of sound has increased? Well, the first harmonic with two open ends looks like this. So I know I have to have a node in the middle and two antinodes at either end. Okay. The wavelength, therefore, has to be determined by the pipe dimension only. If we have a harmonic formed, it has to take this shape. I therefore know that the wavelength is being determined by the pipe dimension. Now the pipe is the same pipe before and after, so the wavelength has to be unchanged. So we know it's A or D. And then I know that speed of a wave is equal to frequency multiplied by wavelength. If I rearrange that for frequency, because that's the other thing I have to check, it's V over lambda. I've said that lambda is fixed. So if V, the speed, has increased, then the frequency must also have increased, giving me A. Question 13. What are the changes in the speed and the wavelength of light when it passes from water to air? So obviously air is less dense than water, so the refractive index of water is larger than the refractive index of air. I know wave speed is frequency multiplied by wavelength. Wavelength, therefore, is wave speed over frequency. Now, I have not changed the frequency of my wave source just because I've changed the medium. So frequency is constant. We discussed this before in class. So if f is constant and the speed increases, and we know the speed increases because we're moving into a less dense medium, the wavelength must also increase. Question 14. A sound wave has a wavelength of 0.2 meters. What is the phase difference between 2 points along the wave which are 0.85 meters apart? So I take the distance between my 2 points, I divide it by the total wavelength, and I therefore know that the 2 points are 4 1/4 wavelengths apart. Okay. If I then look at this diagram and I map out my different phase points, I can see that 1/4 of a wavelength corresponds to a 90-degree phase shift, and so I choose answer C. Question 15. A pair of slits in a double slit experiment are illuminated with monochromatic light wavelength 480 nanometers. Don't forget to multiply by 10 to the minus 9 to convert that into meters. The slits are separated by 1 millimeter. What is the separation of the fringes? S, when observed at a distance of 2 meters from the slit. So this is just using your double slit equation that's in your data booklet. We've got wavelength, we've got big D is the distance between the slit and the screen, and then little d is your slit separation, that's 1 millimeter. That's just plugging numbers in, and what you're really getting the mark for here is your manipulation of powers of 10. So hopefully you've got that right. You can pause and have a little look at the numbers if you didn't, but it should be pretty straightforward. Okay, question 16. For a real cell in a circuit, the potential difference is at its closest to the EMF when? So I've sketched out a circuit where we've got internal resistance and we've got load resistance. Terminal PD can be measured with a voltmeter across the circuit. EMF is the lost volts due to the internal resistance. Now obviously EMF is the total value of voltage required to drive a charge around a complete circuit. Okay, now the main circuit, the external part of the circuit, will be able to receive that full value when the smallest amount of energy is dropped across the internal resistance. So that again is just a bit of a memory one for you there. 17. A long straight vertical conductor carries a current upwards, so I've used my right hand grip rule to get my magnetic field direction here. If I'm to the right of the wire where the electron is, at that point the field is going into the page. What is the direction of the magnetic force on the electron? So I have a moving electron to the right, which means that the current flow, remember because it's opposite to conventional current, because it's a negative charge, is to the left. So I have my field into the page, I have my current to the left, I use my left hand rule, and I can see that I've got, so first finger into the page, current, you can't now see that, to the right, which means that my thumb points down the page. So I just use downwards. Question 18 is a proportionality question. It says you've got two wires made of the same material and have equal length. The diameter of X is twice that of Y. I know that resistance is proportional to length, but they both have the same length, so that doesn't matter. But it's also that resistance is proportional to 1 over area. Now the area of the wire, because it's obviously a cross-section that's a circle, is pi r squared, which is pi d over 2 squared, which gives me pi d squared over 4. So therefore, because pi and 4 are constants, resistance is proportional to 1 over d squared. Now for x, my d value is actually 2d. So Rx is proportional to 1 over 4d squared. And then for y, obviously it's just d, so I've got 1 over d squared. So the ratio of Rx to Ry is going to be a quarter over 1, which gives me a quarter. Okay, 19. We have to use Kirchhoff's laws here to get this right. Resistors of resistance RR and 3R are connected to a cell of negligible internal resistance. So this is not internal resistance. The diagram shows 3 currents, X, Y and Z, in the resistors. Now it would be really easy to go, oh, I've got 3 resistors in parallel because they look like they are, but you need to be careful. You need to trace the path from one side of the cell to the other. Now I can either go through this resistor plus this resistor, or through the 3R resistor and the R resistor. This one is in series with either this one or this one, not parallel. So I know that I have current coming out of the cell IX, and it splits at this first junction, so IX must equal IY plus IZ. I also know that this resistor is going to take a fixed voltage, and therefore when I get a voltage from my cell, I'm going to drop a set amount of voltage through this R and then through this R, and therefore the voltage drop across this one must also equal the voltage drop across this one, because I know that both of those paths mean that I have to drop a fixed voltage value across this one. So I know then that because I have the same voltage drop across this resistor and this resistor, and V equals IR, if I have 3 lots of the resistance here, I must have a third of the current for the voltage across this one and this one to be the same. Okay, so the IZ value must be a third of the IY value such that the voltage across both of them is the same. So IZ is a third IY. I can just express that as IY equals 3IZ, and that gets me B. Halfway, we're there. So 20, 3 fixed charges, plus Q, minus Q, and minus 2Q are the vertices of an equilateral triangle. What is the resultant force on an electron at the centre of the triangle? So remember that force is field strength per unit charge. We've got the same unit charge for each electric field that's being set up. We know then that the force on the electron from each of these minus Q, plus Q, and minus 2Q must be proportional to the value of the field strength. That is dependent on the size of the charge, so this one is going to give a field strength that is double in magnitude to these two at any given point. So because it's an electron, we know it's going to be attracted to this one, it's going to be repelled by this one, and it's going to be repelled by this one. That therefore tells me that the force towards Q is going to be the same in magnitude, because I'm equidistant from plus Q and minus Q, so the force of attraction here is going to be the same value as the force of repulsion from minus Q. Okay, so I've got, this is your minus Q force, this is your plus Q force, and then I know that if my electron is here and minus 2Q is here, the line that the field is running through where the electron is points in this direction. That force is going to be repulsive, so it's going to act down, and it's going to be twice the value as either of the other two. Okay, when I then pick up my vectors and move them around, hopefully you can see that what I end up with is a vector that looks like B, and that's the easiest way that I think you can do that question. Let's go to 21. So, gravitational field strength at the surface of the planet of radius r is g. A satellite is moving in a circular orbit at a distance r above the surface of the planet. So remember that the actual total distance is 2r if we are r above the surface. What is the magnitude of the acceleration? So, g, remember, is acceleration due to gravity, and it's gm over r squared, negative obviously to indicate attraction. So g is proportional to 1 over r squared. If we've doubled our distance from the centre of the planet, then g must be changed by a factor of 4, because 1 over 2 squared is 1 over 4. Okay, 22. A mass at the end of a string is moving in a horizontal circle at constant speed. The string makes an angle theta to the vertical. What is the magnitude of the acceleration of the mass? So because it's horizontal, we know that we can ignore any vertical components. What we do need to do is find the component that is acting towards the centre of the circle, because that gives us our centripetal acceleration. To do that, we need to consider the fact that we have weight, and therefore my vertical component of my tension in the string must equal mg, so that I have no resultant vertical force, and the horizontal component of my tension must be my resultant force towards the centre of the circle. So hopefully you can see that as I'm moving through the angle, this is going to be t cos theta, and this upwards has to balance the down, so t cos theta must be equal to mg. I can rearrange and get an expression for t. T is mg over cos theta. I can then sub this in to the t in my horizontal component equation, because I now know that t is mg over cos theta. So t sine theta must be equal to mg tan theta, just by using my trig identities. Now, I know that acceleration is force per unit mass. My force is mg tan theta, I've just worked that out. If I cancel the m's, I get g tan theta. Question 23. Planet X has a gravitational field strength of 18 newtons per kilogram at its surface. Planet Y has the same density as X, but 3 times the radius of X. What is the gravitational field strength at the surface of Y? Okay, so I know that little g, acceleration due to gravity, it's a minus, but that's just for attractive purposes. Gm over r squared. G is a constant, so little g must be proportional to mass over radius squared. Mass, in terms of density, is density multiplied by volume. It's a planet, we can assume it's a sphere, so the total mass will be density, rho multiplied by volume, 4 over 3 pi r cubed. So therefore, the mass is proportional to the density and proportional to the radius cubed. Okay. So, I know that I have my density value being the same, so therefore the only thing I'm interested in is the radius cubed bit, okay, because rho is the same for both. So the mass of y must be 3 times the radius cubed times bigger than mx, giving me 27 mx. Okay, I also know that not only am I proportional to the mass, I'm inversely proportional to r squared. So, because again, I know that ry is 3 lots of rx squared, I know that ry squared is going to be 9 times bigger than rx squared. So, proportionally, I have a 27 over 9 value of gx for gy, which gives me 3gx. I'm told the initial value for gx is 18, and 3 lots of 18 is 54. Okay, 24. A satellite is moving at a constant speed, so therefore the resultant force is 0. Sorry, the resultant force is not 0. It's been a long morning already. It's a constant speed. That's the crucial bit. That's what I meant to say. So because we have a constant speed and it doesn't say constant velocity, the direction can be changing, okay? And therefore, we don't have a resultant force that is 0. Okay, we have circular motion. At any given time, the resultant force on the satellite is going to be directed towards the centre of the circle of orbit, and that is provided by the gravitational attraction from the Earth. So therefore I get answer B. 25, again this should be a really quick one. Clearly it's circular motion, we always direct our force to the centre of the circle, so therefore choose A. In 26, we have a spring loaded with mass m, and it's oscillating with simple harmonic motion. The amplitude of the motion is A. The spring has total energy E. What is the total energy when the mass is increased to 3m and the amplitude is increased to 2a? So the total energy in simple harmonic motion, this is in your data booklet, is a half m omega squared x naught squared, where x naught is your maximum displacement, so it is your amplitude. So if x naught doubles, then x naught squared is multiplied by 4. The mass has been multiplied by 3. So I've got a factor change of times 4 times 3 gives me times 12, so I choose C. In 27, when monochromatic light is incident on a single slit, so it's single slit diffraction patterns forming on a screen, we're using our single slit diffraction equation, theta is lambda over b. We're told that the width of the slit is decreased. Clearly less light can get through a smaller slit, so the amplitude goes down and the intensity goes down, so we choose B or D. Then we need to look at the intensity and the changes in the width. So the width is represented by theta, to the first minima in single slit diffraction. So theta is lambda over b. If b has decreased, then theta must have increased, and that gives us b. Okay, 28. So this is looking at the last little bit of the wave phenomena we looked at before your mock. So we've got double slit interference. We then look at it on the screen, but remember we started off by looking at the pattern of maxima and minima from the interference, but then we discussed the fact that actually each slit itself will undergo single slit diffraction, and so we get a single slit diffraction envelope over the top of our interference pattern from the double slits. It's a modulated double slit. You should have chosen D. 29. For fringes to be observed in a double slit experiment, the slits must emit waves that are coherent. What conditions are required for the frequency of the waves and the phase difference so that the waves are coherent? This should be really straightforward. We know that we want to have the same frequency and the same constant phase difference between the waves so that they remain coherent by definition. That should be a really quick one. In question 30, we've got blue light is incident on two narrow slits. Constructive interference takes place. The blue light is replaced by red light, so it is expected that you remember the magnitude of different colours in the visible spectrum, and so we know that blue light has a smaller wavelength than red light. What additional change is needed so that the lines of constructive interference remain in the same angular positions? So we take n lambda is d sine theta, we rearrange, we get sine theta is n lambda over d. For sine theta to remain constant, which is what we need for the angular positions to remain the same, if we have shifted to a larger wavelength, because red has a larger wavelength than blue, then this value has got bigger. Proportionally, this also needs to get bigger so that the ratio remains the same. So D must increase, so the slit width must, the slit separation must be further apart. Okay, 31, we're getting there. The two graphs below represent variation with distance d for electric field and potential. You should have remembered that potential gradient is electric field strength. Well, field strength generally, but in this case electric field strength. Okay, so I know then that my potential over my distance must be field strength. Okay, I can rearrange that and say then that potential must be field strength multiplied by D. You can see I've got field strength and I've got D. If I have to multiply those two, I get the area under the graph. It's asking for the work done in moving a test charge. Potential is energy done per unit charge. So because I have a test charge, the potential value is the potential energy value. Okay, and so therefore I can find the area of this, which is field strength multiplied by distance, gives me the potential, which therefore gives me the potential energy change, so the work done. So I'm just finding the shaded area under graph 1. Ran out of space for that one. Okay, 32. You've got a particle with charge minus 2.5 times 10 to the minus 6 coulombs, moves from point X to point Y due to a uniform, important, electrostatic field. You've got some equipotential lines. What is correct about the motion of the particle from X to Y and the magnitude of the work done? So it's a uniform field. E is a constant value, which is force per unit charge. The charge is remaining the same, therefore the force is the same at all points, therefore the acceleration is the same at all points. It's uniformly accelerated. So I choose C or D. I know that the change in potential is going from 300 kilovolts to 700 kilovolts. It's 400,000 volts. I know that work done is change in potential multiplied by charge. I multiply my two values together, the potential I just calculated, the change, and the charge which you're given in the question, and that gets you 10 to the minus 1. and that is obviously just 1 joule. The negative sign indicates whether it's work done against or to the particle, so don't worry about the sign, you're just interested in the magnitude here. Okay, 33, this is where my post-it note comes in. I'll move it up here so I can pop my post-it note in as well. A planet has a radius r. The escape speed from the surface of the planet is v. At what distance from the surface of the planet is the orbital speed 0.5 v? So, in your data booklet you're given expressions for the escape velocity and the orbital velocity of a mass. I can then say the orbital velocity is 1 over root 2 multiplied by v escape. I have to get rid of the root 2, okay, to get to this point. Okay, let's see if I can squeeze it all in. Yes, I can. So here's my planet with radius r, and at r I have an orbital velocity of 1 over root 2v. I know that because the escape speed at this point is v, at orbital velocity is 1 over root 2 escape velocity. Okay, so I know that this is the value of the orbital velocity I have at point r. I want to know what the distance from the centre of the planet is when that v0 value, the orbital velocity, is equal to half the original escape speed. Now hopefully you can see that if I square these, I get v escape squared is 2gm over r. That should show you why I've got this proportionality. R is proportional to 1 over v squared, because 2gm are just constants. Okay, so v is proportional to 1 over root r, therefore r is proportional to 1 over v squared. Okay, and I know that I originally had v over root 2, and I want to end up with v over 2 because 0.5v is just a half v. So therefore, to get from here to here in value, I have to multiply by root 2 over 2. Pause and have a think about that. If I multiply this by root 2 over 2, I will get v over 2. I know then that because my velocity has to be multiplied by this value, v squared is just going to be shown by root 2 over 2 squared. And r is proportional to 1 over the new velocity factor squared. That's just then simple maths. Okay, so root 2 squared is 2, 2 squared is 4, so I get 1 over 2 over 4, which is 4 over 2, which is 2r. Okay, so that tells me that my orbital speed will be 0.5v at 2r. Okay, but it asks at what distance from the surface of the planet. So I'm going from r to 2r, and that's a difference of just r. There's loads there to catch you out, so you should have chosen r. 34. A satellite of mass m orbits a planet of mass big M in a circular orbit of radius little r. What is the work done to move the satellite from r to 2r? So remember, the potential energy of a satellite at any given point is given by minus gmm over r. Additionally, it also has kinetic energy, which is a half mv squared. Now remember from our circular motion that if the satellite is moving in a circle, we know the resultant force is gmm over r squared, but it also is equivalent to mv squared over r because it's a circular motion centripetal force. So the m's cancel, and I can rearrange and say v squared is gm over r. So back to my kinetic energy of my satellite, if I replace the v squared here with gm over r, I know that my kinetic energy is a half gmm over r, and I'm just simplifying how I'm writing that and saying gmm over 2r. So in total, the satellite has both potential energy and kinetic. Remember, kinetic energy is positive, potential energy is negative by definition. So the total energy at point R is the potential energy, the kinetic energy, gmm minus 2r, over 2r, minus the potential energy, because it's a negative number, so when I add them together it's taking away, and obviously GMM over R is the same as 2 over 2 GMM over R. So therefore my total energy is minus GMM over 2R. Okay. I know that my radius is doubling. So therefore, if I multiply R by 2, I'm seeing a factor here. So you can see what I've done is I'm going to say my total energy is minus GMM over 2R. To get that where I have it in terms of 4 on the denominator, 2 over 4 is a half. Okay, so these two things are equivalent. So if I then go from distance R to distance 2R, my R value doubles. Okay, and I can see that when I plug this all in, at 2R I have minus GMM over 4R. So I initially had this much energy. Let me use a different colour. Okay. I then move to distance 2R, and at which point I have this much energy. The work done is the difference between these two. Okay, and when you do that, you're going to find that it's a quarter GMM over R, so you should choose C. It would probably be helpful to pause, have a look at the steps, because there's a lot of manipulation of the equation there. Okay, we're almost there. 6 to go. 35. The diagram shows equipotential lines around two sources. There are no equipotential lines between the two. So I know then that the field has to cancel out between the two. So I either have field lines pointing towards each other, or I have field lines pointing away from each other at that point. Now obviously if we have two masses, the field is always going to be attractive, so I'm always going to have pointing away from each other. So that's a possibility. Two equal masses between the two would cause field lines to cancel out. There would be no equipotential lines. If I have two charges of the same sign, positive and positive, obviously I get repulsion here, I get repulsion here, they will cancel each other out. Two negatives, I'll get attraction, attraction, they will also cancel each other out, therefore would produce no field here and no equipotential lines. So I know then that 2 is also correct. But if I have opposite signs, I'm going to get repulsion, I'm going to get attraction. These add as they are in the same direction. That's not going to work. We would get a resultant field. We would therefore get potential lines. 36. The diameter of a particular nuclide is 12 femtometers. So remember that that tells me it's the diameter. The radius, I should have said, is 6 femtometers. What is the nuclear number of X? So we take our equation from the data booklet. R is R0, A to a third. We're looking for A. So we can rearrange and say R over R0 is A to the third. So R over R0 cubed is A. So I take my 6 femtometers. I divide it by my Fermi radius, which is a constant in your data booklet. The 10 to the minus 15s cancel. 6 over 1.2 is 5, and 5 cubed is 125. 37. So we have a photon of wavelength lambda. What are the energy and the momentum of the photon? Again, this is kind of one that you just need to remember. We know that E equals hf for a photon, and frequency is wave speed over wavelength, so therefore hc over lambda. We know that the de Broglie wavelength are given by words failing me here. Lambda is equal to h over p from our de Broglie equation. So therefore, momentum p must be h over lambda. So it's just a case of remembering your equations, making sure that you rearrange them properly, and you choose answer A there. Oh my, talking for too long here. 38. So Rutherford, Geiger, Marsden, you need to remember that's the alpha particle scattering through gold leaf. We know that that was what gave us evidence for the nuclear model of the atom, and we know that in that case we had most alpha particles going straight through, nothing happening to them. That's what it shows. Okay, it does not show that it doesn't obey Coulomb's law. There was some repulsion when alpha particles got close to the charged nucleus. There's clearly not a fixed nuclear radius, different nucleons in value for different elements, and it's not about the Bohr model of the atom being confirmed either. Okay, 39. Photoelectric effect. We've got a beam of light incident on a metallic surface. The metal isn't changing, so the work function is constant, so that energy requirement remains the same. The graph shows how the current varies with the potential difference with 3 different beams at different times. So remember that electrons are being emitted from the plate because they've been irradiated and the photon has transferred energy to an electron. Electrons leave. A voltage is then put across the circuit between these 2 plates, one of which that's emitting electrons, such that it opposes the motion of the electrons. It slows them down. At the point where the voltage, or the stopping potential value, is equivalent to the energy, kinetic energy that the electron has, the electron will stop at this plate and the current will reduce to 0. So, when current is 0, this is your stopping potential. Okay, you can see that Y and Z have the same stopping potential value. So therefore, they required the same amount of energy to completely bring them to a stop. And therefore, they have the same kinetic energy maximum. The energy of the photon HF is equal to the work function plus the maximum kinetic energy. So if the work function is constant throughout the experiment and they have the same stopping voltage, so therefore have the same kinetic energy maximum, HF must be the same for both. H is a constant, so F has to be the same for Y and Z. Okay, so that tells me that number 3 is correct. X and Y clearly don't have the same frequency because they have different stopping potential values, so therefore HF is not going to be the same because KE max is not the same. Now, the current value at a particular voltage tells us how many photoelectrons are being emitted. So for a specific voltage value, we can see that the current is different for all of them. Okay, and that tells me that different numbers of photoelectrons are emitted, which tells me that the intensity of the light, so the number of photons basically per unit area, must also have been different. Okay, so Y and Z must have different intensity, and that gives me C. Last but not least, we're almost there. Again, this was a nice one to end with. It's pretty straightforward. It's just a memory question. A particle of fixed energy is close to a potential barrier. Which changes to the width and to the height will make the probability of tunnelling greater? Well, clearly the width of the barrier needs to decrease, so the chance of the particle being able to tunnel through that is greater. We need the width to decrease. Also, the height of the barrier means the energy requirement for the tunnelling to occur will decrease if the height decreases, so therefore we choose D.